Okay, first up to bat we've got number 1 that asks us to balance the following equation. So when we're asked to balance something, all we're trying to do is we're trying to make sure that we've got the same number of each kind of atom on both sides of the equation. So the same number of ions on this side as on this side, sodiums, iodides, hydrogens, and oxygens. So let's go ahead and get started by looking at this molecule here. So let's check our irons. We've got one iron here and one iron there, so that's already pretty good. We don't need to do anything there. Let's check our iodides. So we've got two iodides here, but we only have one there. So what do you think we could do to adjust that? Perhaps we could put a 2 right here. Let's go ahead and put a 2 right there. That gives us two iodides on this side, and with two iodides on that side, we've got now the same number of iodides on both sides of the equation. So that's pretty good. But we're not really done yet because that offset our sodiums. So here we have two sodiums on this side of the equation, but only one on this side. What can we do to adjust that? Well, I wonder if we can put a 2 right there. This gives us two sodiums on both sides of the equation. But now we've got 1, 2, 3 oxygens. Well, the one thing that we can change on this side of the equation is, with the oxygens, is the water. Water is the only thing that has oxygens in it. So if we have 1, 2, 3 oxygens on this side of the equation, we need to have 3 on this side. So what we can do is go ahead and maybe put a 3 right there, so that we have 3 oxygens on that side of the equation. And now the last thing we have to check is our hydrogens. So we've got 6 hydrogens here, and by that what I mean is that each water molecule's got 2 hydrogens, and I've got 3 water molecules. So the total number of hydrogens is 6. So I've got 6 hydrogens on this side, and let's see here, I've got 1, 2, 3 hydrogens on this side. So I need 3 more. Where am I going to get those 3? I'm going to get them from here. And I can do that by putting a 3 right there. So originally I had 1, 2, 3, 4 hydrogens. That was before I put the 3 there. And that wasn't enough. I needed 6. So I went ahead and put a 3 right there, and that gave me 6 hydrogens. This was a very convenient place to adjust the hydrogens because it didn't offset any other element. It was just changing the number of hydrogens all by itself. So let's go through and make sure we've got the right numbers of all the elements. So on this side we've got iron. And how many irons do we have? We got 1 there. And we have 1 iron on this side. So that checks. That's good. How about sodium? We've got 2 sodiums on this side and 2 sodiums on this side. That's good as well. Next is iodide. So we got 2 iodides on this side and 2 iodides on this side. That checks pretty well. We got 6 hydrogens on this side, and 1, 2, 3, 4, 5, 6 hydrogens on this side. Good. And finally we got 3 oxygens on this side, and 1, 2, 3 oxygens on that side. Oxygens, we got 3 on this side, and oxygen, we got 3 on that side. Perfect. So everything is good. And then the last thing I wanted to keep in mind is the charges. So this is an interesting equation because we've got charges floating around. We want to make sure that the charges are balanced as well. So we've got 3 positive charges on this side, and we've got 3 positive charges on this side as well. So it's excellent. So the positive charges equals 3 on this side, and the positive charges equals 3 on that side. So that checks as well. So the correct answer for number 1 is D. Number 2 asks us to do the same thing, where for number 2 we've got sulfuric acid, H2SO4, and water. And those two are going to react to make this ion called hydronium. And we're going to be left with a sulfate. And now we're asked to, once again, balance this equation. So we have, to start out, let's look at the hydrogens. We've got 4 hydrogens on this side of the equation, and we've got 3 hydrogens on this side of the equation. So maybe a way to adjust that would be to put a 2 right here, because at least that would give us an even number on both sides of the equation. So now we still have 4 here, and now we have 6 hydrogens here. Now we've got to go back to this side and figure out how we want to adjust the number of hydrogens on this side to give us a total of 6 hydrogens, just like on this side. We have a couple ways of doing this. The way I would go about doing it is I would put a 2 right here, and that causes our equation to be completely balanced. So let's look. We got 2, 4, 6 hydrogens, and that agrees with that, so we got 6 hydrogens there. We have 1 sulfur, yeah, and we have 4, 5, 6 oxygens. Let's see here, we got 2, so 2 oxygens and 4 oxygens there. So we have a total of 6 oxygens here as well. So this equation is balanced just like that. But there's one other thing we can do, because this equation here is not one of the answers for number 2. So the only difference between the answers and what we have here is that the correct answer for number 2 is just this equation multiplied by 2. So just taking all of the molar coefficients and multiplying them by 2. That's all I'm doing. So basically, if I had said, instead of putting a 2 right there, I had put a 2 here, and then balanced the rest of the equation, I would have ended up with this one. So both of these are absolutely correct. This one is just twice the amount of this one. And this one happens to give you the right answer for number 2. So the right answer for number 2 is B. But had you done it this way, you would have been totally correct as well. No problems there at all. Moving on to number 3. Number 3 is once again balancing an equation, but this time I think it's a lot simpler. We've got this equation here, and let's start out with the hydrogens. So we've got 2 hydrogens and 1 hydrogen there. So a quick fix for that is just to put a 2 right there. And what that does for us is that gives us 2 hydrogens on this side. So we have 2 hydrogens on this side and 2 hydrogens on this side. So there's 2 hydrogens on both sides of the equation, which is excellent. But we're not done yet, because now we have 2 fluorines on this side of the equation too. Or excuse me, they're fluorides, technically. We've got 2 fluorides on this side of the equation. And we only have 1 here. So a quick fix for that is just to put a 2 right there. And the nice thing about doing that is that it doesn't offset anything by putting a 2 right there. It only changes the number of fluorides you have. So you've got 2 fluorines and 2 fluorides here, and 2 hydrogens and 2 hydrogens there. So let's just go ahead and write that out. So hydrogens, you got 2 here, and hydrogens, you got 2 there, and fluorines, you got 2 of them here, and fluorides, you've got 2 of them here. Perfect. So both of these match, and so the correct answer for number 3 is D. So number 4 asks us to determine what the molecular weight is of this molecule. In order to do that, what we're going to have to do is visit the periodic table and see what each of the atoms that make up this molecule, what each of their atomic masses are. So to start off, we've got iron, sulfur, and oxygen, and we can just go to the periodic table and see what those molar masses are. So we got 55.845 grams per mole for iron, and then 32.065 grams per mole for sulfur, and then 15.999 grams per mole for oxygen. Then the next thing we have to do is look at how many of each of these atoms we have in the molecule. So for iron, we have 2 irons. So let's go ahead and put that down. So we have 2 iron atoms per molecule. All right. And then here we've got 3 sulfates. And for each sulfate molecule, I've got 1 sulfur. So we've got 3 total sulfurs. So 3 sulfur atoms per molecule. Okay, and then the last thing is the oxygen. So we have 3 sulfates, and for every sulfate we have 4 oxygens. So we have a total then of 12 oxygens. We got 12 oxygen atoms per molecule. Okay, perfect. So what we can do now is we can go ahead and take all of these. Let's see, how do I want to do this? I'm going to go ahead and multiply these out. So just to show you every step, and we've got the total here, Fe2 is going to weigh, and let me get my calculator out because this is by no means mental math. We got 55.845 times 2, because we have 2 of them. We got 111.69, so 111.69 grams of iron per mole of Fe2SO4 Okay. And now we've got the sulfur, so we've got 3 sulfurs. That's what I'm denoting here, is that I've got 2 irons here and I've got 3 sulfurs in the molecule. So now I'm going to take this and go 32.065 times 3 sulfurs, because I got 3 sulfurs in every molecule. So the contribution to the mass there is 96.195 grams of sulfur per mole of Fe2SO4 And then the last thing is the oxygen, and we have to remember we got 12 of these oxygens. So I'm going to go ahead and go 15.999 times 12. And I have 191.99 grams of oxygen per mole of this molecule. Perfect. And so here we go. Let me go like this. Now what I'm going to do is I'm going to take all of these and I'm going to add them up. So I got the oxygen in my calculator already, and I'm going to go plus 96.195 plus 111.69. So by adding all of these up, what I'm saying is I've got 399.87 grams of all of these elements combined, all these atoms combined, per mole of Fe2SO4 So when we say we're talking about the molecular mass, we're talking about the mass of 1 mole of this molecule, which is the individual masses of all of the elements combined. There we go. That's what we've done. So we've combined the number of atoms times their atomic masses, and so we get this number at the bottom, and so that corresponds to A for number 4. So the correct answer for number 4 is A. Number 5 asks, what is the mass in grams of 0.005 moles of cholic acid? And so here's the chemical formula for cholic acid. You don't need to worry about it being called cholic acid, but just here's the formula. That's all we need to know. And what we're going to do with this formula is exactly what we did for number 4, except with the elements carbon, hydrogen, and oxygen. So we'll go ahead and work that out. So we got carbon from the periodic table, has an atomic mass of 12.011 grams per mole. Hydrogen is 1.0079 grams per mole. And oxygen is 15.999 grams per mole. Okay, and what we're going to do is just multiply them by their abundances in the molecule. So we got 24 atoms, so 24, carbon atoms per C24H40O5. Okay, and we have 40 hydrogen atoms and we have 5 oxygen atoms. Okay, and then we're just going to multiply this out, and we're going to add them just like we did on number 4, but I won't bore you with that. But you can certainly practice that yourself and compare it to this. So what I would get when I did this would be 408.56 grams. So this is grams of C24H40O5 per mole. Okay. Excellent. So now we're at grams per mole. So this is the molar mass. It's the mass of 1 mole of cholic acid. The next thing we need to do is we need to revisit the question and see what it is actually asking. It's asking us to find what 0.005 moles of cholic acid will weigh. So if we know how much 1 mole is going to weigh, then what we need to do is just figure out how much 0.005 moles is going to weigh. And this is something we have done many times already this semester. And we're going to take 408.56 grams of, let me abbreviate this. This is going to be C for cholic and A for acid. So Ca is cholic acid. Okay, so this is the molar mass per mole of cholic acid. And we're just going to go like this, times 0.005 moles of cholic acid. And our moles can cancel, and we're left in grams of cholic acid as our units. So the correct answer, when you work this out, turns out to be 2.04 grams of cholic acid. And that corresponds to B. So B is the correct answer for number 5. Okay, number 6 says approximately 70% of a commercial bulking powder is cornstarch. If a scoop of this powder is 334 grams, how many moles of cornstarch are in this powder? So we've got 1 scoop, and 1 scoop is 334 grams of the powder. But we know that we're only interested in the cornstarch, because what we're trying to figure out is the moles of cornstarch in a scoop. So a key piece of information here is that only 70% of the bulking powder is actually cornstarch. So when you take up 334 grams in a scoop of bulking powder, what you have is only 70% of that as cornstarch. So only 70% of 334 grams is pure cornstarch. The rest is just whatever else is in the bulking powder that we don't need to worry about. So the only thing we're concerned about is the cornstarch, and only 70% of that is the cornstarch. So let's start out by doing this. So 70.0% of 334 grams is just simply going to be 334 times 0.7. And let me plug this into my calculator really quick. And that's going to give me actually 233.8 grams of cornstarch. So this is the mass of cornstarch that we actually have. This is the actual mass of cornstarch per scoop. So every time we take up a scoop, we've got 233.8 grams of cornstarch. Okay, so for the actual question, what we're trying to figure out is the number of moles. So what we have to do in order to figure out the moles is we need to determine the molar mass of cornstarch. And we can do that by looking at the chemical formula. And the chemical formula here is C27H48O20. So this is telling us that in one molecule of cornstarch, we've got 27 carbons, 48 hydrogens, and 20 oxygens. So we can do just the same thing we did for numbers 4 and 5 to determine the molar mass of cornstarch. And just look on the periodic table and go, okay, carbon has this mass for every mole, a mole of hydrogen has this mass, a mole of oxygen has this other mass, and you multiply each of those by the number of them that are in the molecule, and then just add them all up together. So I'm not going to go through all of that arithmetic here because we had plenty of practice with that on numbers 4 and 5, but I will give you the final mass that you end up with. So the molar mass, but I would encourage you to practice this certainly because it's definitely legitimate material for a quiz or the exam. So you've got the molar mass here of cornstarch, and it's going to be, I'm going to go ahead and write down 692.654 grams per mole of starch. Okay, so that's our molar mass. And now we're back to square one. We're doing exactly what we've done on previous problems, where we have the mass of our cornstarch, and we're trying to figure out how many moles that mass is. So if we know that the mole of cornstarch is going to be 692.654 grams, and we only have 233.8 grams, then what we can do is just figure out the number of moles that's going to be like this: 233.8 grams of starch times for every 1 mole of starch, there are 692.654 grams of starch. So you notice how I did this. I set this up so that the units are going to cancel. Here we go. Grams of starch cancel. And the units I'm left with are in moles of starch, just like that. So if I do this division here, what that's going to give me is 0.338 moles of starch. And that corresponds to B. So the correct answer for number 6 is B. Number 7 asks us to determine how many molecules of cornstarch this is. So to determine the molecules of cornstarch, what we can do is start with the moles, and we know that from number 6, 0.338 moles of starch. And we have to remember that a mole it represents 6.02 times 10 to the 23rd. So if we want to figure out how many molecules that is, we're just going to plug this in like this, 6.02, and I'm going to give it another sig fig, 6.022 times 10 to the 23rd molecules, 6.022 times 10 to the 23rd molecules of starch. Okay, molecules of starch for every 1 mole of starch. And notice once again, units cancel, and my units are now in molecules of starch. So the answer for number 7 turns out to be 2.03 times 10 to the 23rd molecules of starch. And that corresponds see here, that corresponds to A. So the right answer for number 7 is A. Number 7 has a typo. I noticed that it has a typo here. A actually says 2.33 times 10 to the 23rd atoms. Or excuse me, molecules. So just ignore this typo. If you did the math like this, you should get 2.03 times 10 to the 23rd, and that's okay. But the most correct answer in either case would indeed be A. So that's number 7. So number 8 gives us this reaction, and it's a reaction of a simple sugar burning in oxygen, and it asks us to balance this equation, essentially to identify which of the following, A, B, C, or D, is the correct balanced equation, and we'll just go ahead and balance it here and see if it matches one of the answers. So we have this reaction. I won't tell you what it's called, but I'd recommend knowing what it's called. We got sugar and oxygen burning to make water and CO2. And what we got to do is balance it. So we have 6 carbons here. Let's go ahead and look over here. We got 1 carbon here. So we can conveniently just put a 6 right there, and the carbons should equal. So we got 6 carbons here and 6 carbons there. Good. Carbons are good. Now let's take a look at our oxygens, because that's just the next thing I see here. So we got 13 oxygens on this side of the equation, and then on the left side we've got 8. We got 6 and 2 right here, so we have a total of 8 oxygens on the left side. Well, let's see. Maybe if we turned this into an even number, that would make things a little bit easier. So let's take a look at the hydrogens first, then we'll do the oxygens last. So we've got 2 hydrogens here, and we've got 12 hydrogens there. Okay, that makes it really easy, so we just can put a 6 there, and now we've got 12 hydrogens here, and 12 hydrogens there. Perfect. Hydrogens are done. Now let's revisit the oxygens. So we have 12 plus 6, we got 18 oxygens there. And we have 6 and 2, we have 8 oxygens there. So I think that the best strategy for adjusting the oxygens is to put a coefficient in front of this one, because by changing what this is, we don't offset any other elements. So let's go ahead and see if there's a number we can put in front of this oxygen, this O2, to balance out the oxygens. So what we want is let's see, let's go back here, 6 and 12. So we want 18 oxygens, and we only have 6 here. So let's go ahead and put a 6 right there. And what that's going to do for us is that's going to give us 12 plus 6. Hey, look, we've got 18 oxygens right there. And we also have 6 plus 12. We've got 18 oxygens there. So for carbons, how many carbons do we have? On this side we have 6 carbons, and on this side we have 6. Good. Carbons are good. Let's check our hydrogens. Hydrogens, we've got 12 of those on the left side, and it looks like we've got 12 of those on the right side. Excellent. And for oxygens, finally, we got 6 and 12. So for oxygens, we have 18 oxygens on the left side, and 6 plus 12, and we've got 18 oxygens on the right side. Boom! We've got a balanced equation. And this right here corresponds to the answer A. So A is the right answer for number 8. So number 9 is a little bit more interesting, because here we've got sort of piggybacking off of number 8. So from number 8, we need the balanced equation. So let's go ahead and rewrite the balanced equation. We've got C6H12O6 plus 6 O2s gives us 6 waters and 6 CO2s. Okay, we have the balanced equation. And number 9 says, based on your answer from question 8, how many grams of oxygen are needed to react with 50 grams of sugar. So here we go. This is what we know. We have 50 grams of sugar. And what we need to figure out is how many grams of oxygen we need in order to fully react with 50 grams of sugar. The strategy that I use for solving problems like this is to start out going from grams of sugar to moles of sugar, and then I'm going to go to moles of oxygen, and finally then to grams of oxygen. So what I'm going to use here is I'm going to use the molar mass of the sugar, and then going from moles to grams, once again, I'm going to use the molar mass of oxygen. Okay, so let's see this actually in practice. How do we actually go about doing this? We got grams of sugar. That's given to us. There's our 50 grams of sugar. That was easy. And now we need to know what the molar mass of the sugar is. So from the molar mass, the molar mass, you can either look it up because this is a fairly popular or fairly common formula, or you can calculate it just like we did for the previous problems where you got the atomic masses of each of the elements, and you know how many elements or how many atoms of each element you've got in the molecule, and you add all those up together. That works perfectly well too. You'd get the same answer. So I'm just going to go ahead and give you the molar mass for the sugar, and that's going to be 180.156 grams. So here, watch this. We got 1 mole on top. 1 mole of sugar. That goes on top because I want my grams of sugar to cancel. We got 180.156 grams of sugar. Okay, and there we go. Grams cancel. And I'm left with moles of sugar. So now I'm at this stage right here. I've got moles of sugar. Now I got to figure out how many moles of oxygen there are. And this is where the equation comes in really handy, because from the equation I can glean a lot of information about mole to mole ratios. I'm looking at the equation here, and what the equation's telling me is that for every 1 mole of sugar I need exactly 6 moles of oxygen, of O2. Exactly 6 moles of O2. So 6 moles of O2 react with 1 mole of sugar. That's really important. And this is what that equation tells me. So I can incorporate this into this part of the stoichiometry, where I'm now converting from moles of sugar into moles of oxygen. So I'm going to convert into moles of oxygen, and I'm going to say 6 moles of oxygen, of O2, for every 1 mole of sugar. I got this from the equation. Okay, from the equation. That's where I get this. This is called a mole to mole ratio. So I got for every 1 mole of sugar, I've got 6 moles of O2. So that has to come from the equation. And it has to come from a balanced equation. That's why balancing equations is so important. And that's where you get this number. So you got 6 moles of O2 for every mole of sugar. Once again, our moles of sugar cancel. And lastly, we're going to use the molar mass of O2 to figure out how many grams there are in this many moles of O2. So the last step is, I'm going to go ahead and just make this explicit here. I've got 2 times 15.999 grams of O2. Okay, I'll explain that in a second. Per mole of O2. Okay, and we're done. That gives us now grams of O2. So why did I put this 2 here? I put that 2 there because it's O2. There's 2 oxygen atoms in there. So each atom, a mole of each atom, oxygen atom, weighs 15.999 grams. But since it's O2, I have to take that into account that I've got 2 oxygen atoms in a molecule of O2. So the molar mass of O2 is going to be 2 times 15.999. And that's going to be about 32. Okay, so and then when I run through all of this stoichiometry, I got to make sure all my units cancel. Yep, and then moles of oxygen are going to cancel just like that. And I'm going to be left with grams of oxygen. So the final answer for this is going to be 53.34 grams of O2. Okay. And that would correspond to answer B. So B is the right answer for number 9. Alright, so for number 10, we have here an equation where we're combining iron and oxygen to make rust, Fe2O3. And before we get going, let's make sure that we have a balanced equation. So we have 4 irons, 4 irons, and 6 oxygens. Looks good to me. Good, so we have a balanced chemical equation, and the question is asking how many milligrams of rust, so what's the mass of rust basically, are made from 25 kilograms of pure iron metal. So the strategy I'd like to implement for this kind of a problem is the same thing that we did for number 9, where we're going to start with the mass of iron, and we're going to convert that into moles of iron. And we're going to do that using the atomic mass of iron. Then what we can do is go from moles of iron into moles of Fe2O3. That's the nice thing about working in moles, because what you can use for that is the balanced chemical equation. We'll see all of that play out as we get going. And finally, from moles, we can calculate the grams of Fe2O3. And what we're going to use for that is the molecular mass of Fe2O3. All right, so let's actually see this happen. So starting out with the mass here is 25 kilograms. That's how much iron metal we have. And in order to find the moles and use the atomic mass from the periodic table, what we want to do is we want to use grams for the iron. So we're going to go ahead and convert this into grams. So we're going to go 1,000 grams in 1 kilogram. Now we can use the periodic table. So for every 1 mole of iron, we have 55.85 grams of iron. Perfect. So let's go back and make sure our units are working out. So we got kilograms and kilograms cancel, grams of iron and grams of iron are canceling, and we're left in moles of iron. Good, that brings us to this step. So far so good. Now the next step is to figure out the number of moles of iron oxide that we're going to make. And how are we going to do that? We're going to use the balanced chemical equation to do that. So what does the equation tell us? Let's go back up to the equation and see what it actually tells us. The balanced chemical equation tells us the mole ratio between iron and iron oxide. Essentially what this is saying is that if you have 4 moles of iron, you're going to get 2 moles of iron oxide. So it takes 4 moles of iron to make 2 moles of iron oxide. So your mole to mole ratio is going to be 4 moles of iron to 2 moles of iron oxide. So coming back down here, we can use that relationship to convert from moles of iron into moles of Fe2O3, iron oxide. So here we go, 1 mole of Fe2O3 for every oh, let's see here. Let's just do it this way. 2 moles of Fe2O3 for every 4 moles of pure iron metal. There we go. That's coming straight from the equation. We got right here 2 moles of Fe2O3 and 4 moles of just iron. Okay, so we're in moles of iron oxide, and now we can use the molecular mass of iron oxide to get us into grams. So the molecular mass of iron oxide, which you can figure out from the individual atoms, or you can just look something like this up, that's going to be 159.7 grams of Fe2O3 for every 1 mole of Fe2O3. Okay, and let's go back and make sure all of our moles cancel. We got moles of iron canceling there, and moles of iron oxide canceling there. Perfect. So our final units here are grams of iron oxide. So when you do this calculation, what you end up with is it's going to be 3.6 times 10 to the 4th grams of iron oxide. So notice how it's 10 to the 4th grams and not milligrams. So there actually turns out to be a typo, and the typo is in all of the answers. So on answers A, B, C, and D, where it says grams, you got different numbers, but they all say grams, they should say milligrams. So what we should solve for is the milligrams of iron oxide, because that's what the question was originally asking for. So let's go ahead and do that. So we got 3.6 times 10 to the 4th grams of iron oxide times 1,000 milligrams in 1 gram. So grams are going to cancel, and therefore the answer is going to be 3.6 times 10 to the 7th milligrams of iron oxide. And that corresponds to B. So the correct answer for number 10 is B. Alright, of course, ask me any questions, shoot me an email, come see me in my office hours. I'm more than happy to help you out if you need anything. And so that was worksheet number 5. Alright, take it easy.